So in this video we're looking at musical notes, specifically how musical scales are formed. We're looking at a quality of musical notes called timbre, and we'll be looking at beats, which is this diagram on the bottom right here from the physicsclassroom.com, which is also a great website for lots of other self-learning in the physics realm. So first of all, we've talked about overtones and harmonics, and but I just want to very quickly touch on pipes as an example of how scales can be formed. Because if we look at the fundamental for a closed pipe, remember this in the center is a way of representing the amplitude, transverse sense, the amplitude, positive and negative, that the particles, the medium, can displace. So at this point you've got an antinode where the particles are vibrating up and down with maximum amplitude, and here maximum pressure and minimum amplitude, the basically no amplitude, the particles don't move. Actually, maybe this wasn't the best example to use, but when we go to the next, this is the first note, if you like, that can be played, which is why it's called the first harmonic. First note that you can play, the most fundamental note you can play in an open pipe. If we then, a closed pipe, if we then go to the next note, which is actually the third harmonic, because it's 1/3 the wavelength, we end up, let's see, boom, with, not drawn the greatest, but you can see, so that's got 3 times the amount of wavelength in there compared to the first one I draw. This is the third note that can be played. Well, it's actually the second note that can be played, but it's the third harmonic because of the way that it works anyway. So you've got 3 times the amount of wavelength in there. So this is, I'll write it another way, the wavelength is divided by 3. So we're going to have a note from V equals F lambda. We're going to have a note of a particular frequency, which is going to be 3 times higher, because the velocity doesn't change. The speed of sound, of the speed of the medium that these particles can vibrate at, doesn't change, okay, unless you warm it up, in which case it may change in certain ways. You can look at scholarship physics questions for that if you want, but we're not going to look at that now. It's unique to each instrument. So the speed doesn't change, no change there. We're dividing the wavelength by 3, so we increase the frequency by a factor of 3. So that's just an example of how you can change, produce different musical notes. So in this case you can either blow harder across the top. So you tend to, musical instruments are usually designed with pipes that you blow across the top, or you vibrate a reed, which helps vibrate the air in there. You have to anyway vibrate the air at the opening, and that sets up the standing wave in the column of air. But we can blow harder to produce a higher harmonic or higher overtone, or you can perhaps have different holes open at different places along the side, like you see in like a flute or clarinets have this, and saxophones, except they usually have mechanical levers to cover and open the holes. But when you cover and open the holes, you're changing the length of the pipe, changing the notes. So there's multiple ways you can actually produce different notes. Now I'm going to go to the guitar string, because it's much easier to see, and I should have started with that, but here's our guitar string with the fundamental represented on it between 2 nodes and an antinode in the middle. When we play this, if we play the second harmonic, so it's the first harmonic, if we play the second, we're going to get this pattern, okay, and we're doubling the frequency. Okay, and this is where we get into scales, is that by doubling the frequency, so 2F, if we double the frequency, we actually go, this is really only useful for musicians, we go an octave higher. So if you remember musical notes in our system of measuring musical notes, we have 8 notes in an octave. Okay, so that would be 8, like A, B, C, D, E, F, G, and back to A again. That's because that's A. Let's write that B, C, D, E, F, G, A. That is one complete octave. that has to go from A to A, and for example, this might be 220 hertz. Okay, 220 hertz. I think that's about right actually. And then if we wanted to go to this A, it would be 440 hertz. So by doubling the frequency, as we saw down the bottom here, doubling the frequency by halving the wavelength, or doubling the amount of the wave on the string or in the pipe, if it's an open-ended on both ends of the pipe, we double the frequency. This works the same if you're going from B to B. If you had B in the next year, you double the frequency, and you're going to double the frequency, and you end up a whole octave higher. We've got all the sharps in between in different places as well, but not going to get into that. My musical knowledge is not that strong. I did learn classical guitar and drums. Drums seem more a bit like a physicist with beats and things, but you've got all of this anyway. But anyway, timbre. Timbre is really important. I'm going to go back up because this one will be quick. Timbre is basically a way of explaining the different notes that can be produced, or the different sounds that can be produced, even though they're the same note, by different instruments. So a violin sounds different to a viola or a clarinet or a guitar. Okay, some of that is due to them being stringed instruments, some of it's compared to wind instruments, but a guitar still has a resonating chamber, which is how it kind of amplifies the sound, and that's effectively being a wind instrument, but the string is used to start it off. Very clever, very interesting when you think about it actually. But let's move on because I'll take too long otherwise. So timbre, what it is in each instrument that you play, there is always more than just the fundamental playing. So in this pipe here, this might be we'll just say it's a clarinet because it's easier. A very simple representation of a clarinet or a flute. My wife plays flute. We'll use a flute. Okay, so the flute, you might blow over the opening of the flute, produce the resonance in the column, which sets up a standing wave, and then you might play another flute and it sounds different. Or a clarinet or saxophone, same length of pipe or something, but to produce the same fundamental, but it might sound different. And that's because you've got different overtones playing at the same time. Okay, and if you imagine those waves are all going to add to produce something kind of funky, but the overall fundamental is still going to dominate because that is the longest wavelength and the most easy one, I guess, to hear with our ear. Maybe that's not true. It probably depends on your ability to hear. But the key thing about timbre is that you have different overtones. It could be one or two overtones playing. It could be a whole bunch of them playing over the top to produce a different kind of sound to that initial fundamental frequency. So that's what timbre is. It's very cool. And it's a little bit like fingerprints. It gives a very specific signature like an audio signature to that particular instrument. Very interesting. Anyway, beats. Last thing on musical notes and beats. Beats is an interesting phenomenon, and it's very similar to interference, where if we play two notes at the same time, so this is where we get to our diagram from the physicsclassroom.com. We've got the red wave and the blue wave, and they have a slightly different frequency, very slightly different frequency. And if you look down on here, you can see the blue and the red waves superimposed over each other, and you can see particularly just here that they're out of phase. So at that point, when they add together and to interfere, they're going to produce very low amplitude because they're out of phase. That means a peak would be adding with a trough. In fact, right here in the middle, you've got a blue one down the bottom and a red one up the top. Hopefully the diagram's clear on your screen. But they're adding to produce nothing, and this green overlay over the top of it is showing how they add together and to produce that interference pattern. And what you will actually hear is not the red wave by itself or the blue wave by itself. You'll hear this overlay, and it'll represent a little bit like a thrumming sound, what we call the beat frequency, which it happens to work out very nicely that it's the difference between the red and the blue. So if we were to write that up as a formula, the beat frequency is going to be the frequency of whatever one it is minus the frequency of the other one. So FB, beat frequency, equals F2 minus F1. It's just the difference between the two frequencies. So if this happened to be 220 Hertz, remember Hertz is cycles per second, and this was, say, 222 Hertz, the beat frequency would be 222 minus 220 is 2 Hertz. The only thing this doesn't tell you is which one has the higher frequency and which one has the lower frequency. You need the context of the question to tell you the rest of that. Okay, so the beat frequency anyway is 2 Hertz. Let's just write that in there. Okay, so that's all it is. The two waves overlay, they add. Wherever peaks meeting peaks, they'll cause constructive interference. Wherever troughs meeting troughs, constructive interference on the other side of the axes. Wherever peaks meet troughs, you get cancellation or adding to zero, and then you get zero amplitude for this beat frequency, which are these little bits in the middle. So maximum amplitudes, minimum amplitudes, and overall what you'll hear is over the top of these two notes is this beat frequency. Now this is particularly useful when you're playing guitar, because I know about this from my experience. When you're tuning a guitar, and I guess any stringed instrument, you often play one note on the string above to tune the string below. So once you've got one string tuned properly, I don't know how you get that first string tuned properly, but they often sound good when they're all tuned off one string, but then you go and play with another instrument and it's tuned differently. So you've got to get all the instruments tuned together. That's why you need a standard note. But anyway, so you get the top note, top string of the guitar right. You play a note on that. That's not just the open string. You usually push down the 5th fret. And then you play the string below it, and that string should sound the same as the top string with the 5th fret pressed. And so you have to adjust the keys, tighten or loosen the tension in the string to get the 2nd string down to sound the same as the 1st string with the 5th fret pressed. And what you do is you play them both at the same time and you listen for the beat frequency, and when you adjust the tension so the beat frequency reduces to 0, then you know they're in tune, and you move on to the next string. So that's musical notes, scales, timbre and beats.